So we started with a bit of modeling of dynamical systems. Then we talked about the Laplace transform, the inverse Laplace. We looked at specific cases like first and second order systems. It's high time we talked about stability, which is a notion of central importance when it comes to designing control systems. Here we're focusing on linear dynamical systems with the transfer function g, and we assume that g is given by a rational function p over q times, potentially you may have a delay, e to the minus delay times s. And we assume that this rational function is strictly proper, as we say. So the degree of p is strictly less than the degree of q, which is pretty standard an assumption. So welcome to this video where we'll talk about stability, BIBO stability in particular, where BIBO stands for bounded input, bounded output. This means whenever the input of the system is bounded, it is something like a constant function in time, or it is a sinusoidal function in time, or it is e to the minus t, and so on. So if it is a bounded function in the time domain, then the output is also a bounded function in the time domain. And there are some criteria to tell whether a given transfer function has this property, which is absolutely a desirable property. And the first one is that g is BIBO stable if and only if its inverse Laplace transform, the inverse Laplace of g, which is the impulse response of the system, this is the impulse response, if this is absolutely integrable, which means that this integral of the impulse response exists. It's an integral from 0 to infinity, and it's finite. Of course, this assumes that we have the impulse response. There is this second criterion that doesn't require that you determine the inverse Laplace of g, doesn't require that you have the impulse response, which you may not have. So the second criterion is that g is BIBO stable if and only if the poles of g, what are the poles? They are the roots of q, so we're focusing only on q, have a negative real part. So that's all you need to test. And let's use these two criteria to tell whether some transfer functions are stable or not. So the first one is 7s plus 1. It doesn't matter what you have in the numerator. And then in the denominator you have s plus 1 times s plus 2. Actually, that's wrong. What matters is that the degree of this is less than the degree of this, which is the case. Now, what are the poles of this transfer function? Clearly, we have minus 1 and minus 2. Both of them have a negative real part. They are actually negative real numbers. So yes, this is stable. Okay, moving on. The second one is 1 over s plus 1, s minus 1. So from s plus 1, we have the pole minus 1, and from the other one, we have plus 1. Are they both with a negative real part? No. So this is unstable. The third one says it has 1 over s plus 1 squared, which means that the poles are minus 1 and minus 1 again. It's a double pole at minus 1. That's acceptable. The transfer function is stable. The next one now. The next one has a pole at 0, and it also has poles at plus and minus j on the imaginary axis. They are imaginary numbers. So what are the real parts? The real part of this is 0, and the real part of these two is also 0. 0 is not negative, so this is an unstable transfer function. In the next example here, I'm giving you the impulse response. So the impulse response here is minus e to the minus t. We'll have to apply the first criterion that says g is BIBO stable if and only if little g is absolutely integrable. So take now the integral from 0 to infinity of the impulse response. And you can easily tell that this is less than infinity. Mean you can test it if you like, really. You can do this carefully and you'll see that it's less than infinity. So this is stable. Next, a similar example. Now, I'm not really giving you the impulse response little g. I'm only telling you that this little g is less than e to the minus t, and that g is continuous. I'm telling you that g is continuous so that you don't have any peculiarities with the integral. So this means that your integral from 0 to infinity of the absolute value of your g, okay, is less than equal the integral from 0 to infinity of e to the minus tau d tau. And this integral is less than infinity, which means that, of course, the first integral is less than infinity, which means that this function is also stable. This was a little more tricky. Now, let's have a look at the next example, where we have in the denominator this weird thing, s to the power sixth and so on. It's a sixth order polynomial. There is no way, at least analytically, to determine the poles of this thing. So, unfortunately, the answer here is we don't know. We cannot tell the poles of this transfer function. I mean, we can do it numerically using Python or some programming language, but we cannot tell just by looking at it. And the last one falls in the same category. We have s to the power 3 minus s squared plus s plus 1. I don't know, it's not evident what the poles are here. So again, the answer is we don't know. Enter criterion 3 that says if you have q, which is a polynomial of s, in this form, a naught plus a1 s and so on, up to a to the power an, let me fix this typo, an s to the power n, and either one of the coefficients is 0, one or more of the coefficients is 0, and not all of them have the same sign, then g, which is p over q, is unstable. Which brings us back to this example over here, and if you look at the denominator, it is s to the power 3 minus s to the power 2. So this has a coefficient of 1, and this has a coefficient minus 1. So we're in this case, not all ai have the same sign. So actually, this is now unstable. Of course, that's a special case. And if we go back to the previous example here, still we cannot tell. We cannot apply criterion number 3 and tell whether this is stable. So we need one more criterion. And this is the Routh-Hurwitz table. So first, this is a table of numbers. I'll show you how to construct it, and then I'll tell you why this is useful. So say you have a polynomial q of s, which is given like this. So you have the coefficients. The first thing you need to do is write down these labels. These are useful actually. So this is the label. This is the row which we denote by s to the power n, s to the n minus 1, and minus 2 down to s to the power 0. And then start with the highest order coefficient, put it here, and then fill in the table in a zigzag way, fill in the first two rows in a zigzag way like this. So here goes an, here goes an minus 1, and so on, in a zigzag. Example, take q to be s to the power 5, plus 2s to the power 4, 5s to the power 3, 6s squared, 7s, and then 11 is the constant. So take these coefficients, 1, 2, 5, and put them in the first two rows like this. 1, and then 2, and then 5, and then 6, and 7, and 11 in a zigzag. So that's the first thing to do. And next, we will fill in this part of the table. And the first thing we'll do is that we'll focus on this third row with unknown coefficients. And we'll take it from the beginning. So the first thing to do is to determine this first entry in the table. And this first entry goes like this. It is this number times this number minus this times this, you do a little x there, divided by 2. So it is 2 times 5 minus 1 times 6 divided by 2, and you write it here. This happens to be equal to 2. So, okay, we did this. Let's move on to the next entry to the right. So the next entry is like this. It is 2 times 7. You move the second column here to the right. So you shift it to the right. 2 times 7 minus 1 times 11 over 2. And you write the result here. It happens to be 1.5. There is no next column, so just put a 0 here. And we'll continue now to the fourth row. So we filled in the first two with the coefficients and the third one. Now, in the fourth row, you do exactly the same thing. So 2 times 6 minus 2 times 1.5 divided by 2. And you write the result here. The result is 4.5. 2 times 6 is 12, minus 2 times 1.5 is 3. 12 minus 3 is 9, over 2, 4.5. Right, so we did this, very good. Let's move on to the next coefficient to the right, here. So the next coefficient you do exactly as you did before, as you worked before. So it is 2 times 11 minus 2 times 0 divided by 2. And the result is 11, and you write it here. And there is no next column, so you put here a 0 and you continue to the next row. You see, it's the same procedure. Let's do it once more. Now we are at row s to the power 1. So you do 4.5 times 1.5 minus 2 times 11 divided by 4.5. And you write it here. The result is minus 3.3889. It's a negative number. Then moving on, okay, here you can put a 0 if you must. You do the same thing here one last time to fill in the row annotated with s to the power 0, and you find that this is 11. You have filled in the entire table. Actually, we're interested only in the entries in the first column. Now, by looking at the entries in the first column, we can tell whether the system is stable or unstable. And in this case, it is unstable. Let's see why. This is the Routh-Hurwitz criterion. It says the transfer function is BIBO stable if and only if there are no sign changes in the first column. This means either all entries are strictly positive or all entries are strictly negative. So even if you have a 0 here, this means your system is unstable. What happens here is that we have a positive entry, positive, 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 and then we have a sign change from positive, it goes to negative, and another one actually, from negative it goes to positive. It doesn't matter. What matters is that not all these entries share the same sign, so the system is unstable. Actually, the criterion can tell you also how many roots of Q are in the unstable area, so with a non-negative real part, but I don't want us to go there in this video. So let's have a look at this example. This is from the textbook. This is example 9.8, where you have a polynomial q of x, could be q of s if you prefer, which is 1 plus 2x plus 5x squared plus 3x cubed, and so on. So the first thing to do is fill in the first two rows of the Routh-Hurwitz table, and note here that sometimes you'll have the highest order term written at the beginning, sometimes at the end, or they could be shuffled. So be careful to put always the highest order coefficient here, and then the rest follow in a zigzag manner. So now, if you do the same procedure as we did before, you will find that the entries of the first column are all positive. They're all positive, which means that the roots of Q have a negative real part, which means that your transfer function G, which is P over Q times perhaps some delay, is BIBO stable. And we did this by looking at the coefficients of Q alone. So now we have a criterion that we can apply really to any polynomial, to any transfer function that has this form. Next, in the next video, I would like us to discuss applications of these criteria in control, and in particular in controller design. And well, there is a little catch here with this criterion. You know, the stable area is where the poles have a negative real part, right? You're somewhere here, but this means that this pole, which is extremely close to the imaginary axis, or this pole over here, is also stable. Strictly speaking, it is indeed stable, but it's too risky to be there. Why? Because maybe you have misestimated some of the parameters of your system, and actually you've done mistakes in your you have mistakes in your calculations, you have errors, and in reality you're not here, you're here. So you're unstable. So it's risky to be very close to the edge. So next time we'll also look at the criterion that allows you to make sure that all your poles are sufficiently away from the imaginary axis. They have a sufficiently negative real part. So thank you very much for watching, and see you next time.